We go much better, much better. Okay, the recording started. Oh, the other announcement number 2. In this class, we have someone who has a learning disability who needs a note taker. So we need someone to volunteer to take notes so that the person with a learning disability who needs this as an accommodation for their disability can have those. The Center for Students with Disabilities will cover costs of photocopying. This will also be something you can put on your resume if you volunteer to do this. Just take the normal notes that you take every day and bring them to the Center for Students with Disabilities, and they can cover the photocopying to be given to the student who needs them. Is there anyone here who would, and again, if you volunteer, it'll be something you can put on your resume. It'll also go on your co-curricular record. So is there anyone here who takes, pretty good notes and would like to volunteer to do that? If you're interested in volunteering but you don't want to put up your hand right now, also feel free to come talk to me after class. I know they're going to cover it. I'm assuming they have a photocopier there, and you can just bring it there, and they'll do it. Yeah, for the photocopying. So you can do it.
I can take PDF notes like I write on a tablet, and then just email them.
That
Do they accept that?
I think so. I'd have to ask them about that. But I can't imagine that would be a problem.
Okay.
If that's, that actually would anything would be easier, I can imagine, because they're already, yeah. So. I will, okay, come talk to me after class. If there's anyone else who's interested, come talk to me after class, and I'll work it out then. Okay, so that's it for announcements. So I'm going to move on to the Muddiest Point cards from last class. So there was a couple problem who were talking about, there's a couple people who were talking about that last group problem that I did last class. The one that was find the antiderivative of 2 plus x squared over 1 plus x squared. Right? And remember, I said you can find the antiderivative by breaking up the top thing like this. And then you can do 1 over 1 plus x squared, whose antiderivative is tan inverse. And 1 plus x squared over 1 plus x squared, whose antiderivative is, that thing is just 1, its antiderivative is x. So you can split it up into 2 things and do the antiderivative separately. A couple people asked me to do another example like that, so I'm going to do another example like that. One thing to mention is this difficulty of problem is not something that's going to come up on the quiz on Tuesday, next Tuesday. This is an assignment difficulty problem, at least for now. Later on in the course, you'll learn some other methods for dealing with this. Something called long division of polynomials is a very useful way of dealing with problems like this. Once you've learned that, then it'll sort of, you'll have a more general method for dealing with it. For now, I wouldn't give this to you on a quiz. I'd only give it to you on an assignment where you would have lots of time. Where's the eraser? So, I'm just going to do it right here. So the other one I'm going to do is say you want to find the antiderivative of this guy. 3 plus 2x squared over 1 plus x squared. The goal here is we're going to try to break this up into something that looks like a 1 and something that looks like a 1 plus x squared. Right? Because if you have 1 over this, that's something you could find the antiderivative of. That's tan inverse. If you have 1 plus x squared over 1 plus x squared, then those things can cancel. Well, it turns out 3 plus 2x squared, this I can think of as 1 plus 2 times 1 plus x squared. Right? 2 times 1 plus x squared is 2 plus 2x squared. If I want to make it into 3 plus 2x squared, I've got to add an extra 1 on. Right? So I'm thinking in the 3 plus 2x squareds, there's 2 of these guys. There's 2 1 plus x squareds that go into that. And then there's also another 1 that's left over. So I'm going to write that whole thing as 1 plus 2 times 1 plus x squared. And then I can split that up into 2 separate fractions. The first fraction is going to be 1 over 1 plus x squared. The second is going to be 2 times 1 plus x squared over 1 plus x squared. In this second one, these guys can cancel. So if I want to find the antiderivative, if I want to find capital F of x, again, for antiderivatives, that's usually the symbol we use, is capital F of x. The antiderivative of this guy is going to be tan inverse of x. The antiderivative of 2 we can think of as 2x to the 0, so it'll be 2x to the 1 over 1, which is just 2x. Another way to think about the derivative of 2x is 2. And then you just have to put a plus c on it. So again, to do problems like this, what you have to do is you have to sort of think about the top of this thing as something that looks like a 1 plus something that looks like a 1 plus x squared. Again, the thing to mention about these problems is that these are not, this is like a hard problem right now because I haven't taught you the method of long division of polynomials, which is sort of the systematic way of doing this. So if it was something like this was going to come up on a test, I'd give you a hint for it, like hint, think about the numerator as this, right? Or it might be on an assignment, and I might say, look at this example, try to do this one like this example. You know, I go, so I would definitely sort of walk you through this a little bit. That's going to come up. Any questions about this example? Okay. The other muddiest point which came up, which I'm going to answer really quickly because it's really quick to answer. The question was, is tan inverse x the same as arctan x? And the answer is yes. An inverse on something is the same thing as an arc. Oh, not arctan, arctan. So if arc sine is the same thing as sine inverse. Arc cos is the same thing as cos inverse. This negative 1 is not an exponent. Tan to the negative 1x is not 1 over tan x. This is not an exponent, it's an inverse symbol. They look the same, they have different meanings. Just like a 0 and an O look the same, but they have different meanings. This symbol and a negative 1 exponent look the same, but they have different meanings. So if you see a negative 1 on a tan, on a sine, or a cosine, that means you're doing the inverse function. You're doing the arc of that thing, you're not doing that thing to the negative 1 power. There are a couple other ones that I'll focus on when they come up later. Someone asked about word problems. Once word problems come up, I'll spend more time on them. There aren't really any word problems yet in the course, so you don't have to worry about them for a while. Yeah. Anyways, so any other questions before I get into the new material? Okay, so I'm going to start off section 5.1 from the text. I have handouts for it. There we go. Here, take one, pass from the back. Take one, pass from the back. How many people here have, I just realized, I didn't cross-check this last time, how many people here have taken Math 112 before? Okay, a bunch.
3 years ago count?
Sorry?
3 years ago count?
Maybe. I guess, well, to be honest, what I was really just checking is how many people this is going to be review and how many people this is going to be new. One of the ways I like to teach the beginning of this is I like to teach it in such a way that that people can appreciate how hard it was to do things before calculus was invented. So what will happen in chapter 5, in chapter 5.1 and chapter 5.2, I'll be talking about, how people did things before the 16th century when calculus was invented. 5.3 is where I'm like, now look what calculus can do. So for those of you who have taken calculus 2 before, try to not ruin the surprise for those who haven't, as to how what the easy way of doing these problems is. Now, when it comes time for the quiz next week, well, 5.3 will be covered on Thursday's class, so it'll come pretty quickly. But I just wanted to mention that, yeah, so for the quiz next week, you don't have to do things the hard way, but today's class I will be doing a bunch of problems the hard way to sort of demonstrate for you how annoying the sort of the hard way of doing things is. So the problems I'm going to be solving in today's class is this problem that's called the area problem. So it's something that's been around for mathematicians since the time of, the Greek mathematicians like Euclid and Pythagoras and them. And it's really the problem of how do you calculate the area of a curved shape. Right, now we know, okay, if we had a shape like this, yeah, something like that. We know how to calculate its area because we know how to calculate the area of a triangle, and something like this with straight sides, we can always divide up into triangles, right? Calculate the area of this triangle, calculate the area of this triangle, calculate the area of this triangle, add them together, right? If you have, let's say, a semicircle, right? You can also calculate the area of that one pretty easily. Just take the area of the circle, divide it by 2. Gives the area of a semicircle. The problem is what happens when you get a shape like this. This is supposed to be a parabola, right? So this area is half of the area of a circle. The area of a circle is pi r squared. This one is a parabola. And again, I've sort of cut off the parabola at height so it has an area. We don't have a formula for the area of a parabola. And a parabola is a pretty simple shape. But the key thing is that, straights with straight sides, you can always calculate their area by dividing them up into pieces. Straights with curved sides, if the curved side is not something nice like a circle, calculating the area of it is actually very hard. And it's something that gives Greek mathematicians lots of problems. So again, the parabola is one of the simplest curves that's out there, like y equals x squared, a fairly simple curve. But we don't have a formula for its area, how to calculate the area of it. So what we're going to be talking about in section 5.1 is sort of what approach could we use to try to calculate the area of that sort of thing. So for example, maybe we want to consider, there's a parabola, y equals 2x minus x squared. If you graph it, the graph looks like this. Goes through x is 0 and x is 2. The vertex is at x equals 1. The height of that vertex is 1. So we have this blue area here, right, which is the area between that parabola and the x-axis. And the question now is, how could we calculate this area? And what I'm going to be talking about in today's class is sort of ways that people calculated this area before calculus came around. So how people, can try to figure out the area of like this. It turns out that these methods I'm going to be talking about apply to any curve. It could be a parabola. It could be e to the x. It could be sine x, right? Any function these methods will apply to. But yeah, that's what I'm going to be talking about. That's what the area problem is how do you calculate the area of a shape which has a curved side. So the first thing I'm going to be talking about how to calculate this area is how do we estimate the area? Because the idea is if we can estimate something, if we can approximately, how big it's going to be, that, is a start of a step towards calculating it. So I'm going to talk about how we can use 4 rectangles and left endpoints to come up with an estimate for the area between the curve y equals 2x minus x squared and the x-axis. How many people here remember how to do that because they've taken Math 112 before? Anyone? I see one hand. Is there anyone here who knows they knew how to do it at some point in the past and completely forgotten? So it might be review. Okay, you can see a couple hands. And I'm assuming most of the other people have just... How many people have not seen a problem like this at all before? Okay. Anyways, I sometimes ask these questions about, how many people are familiar with this, how many people are comfortable with this, partly because there are people who have taken the course before. And the idea is I want to focus more on topics that more people haven't seen before or are really uncomfortable with. So oftentimes when a topic comes up, I will be asking those sorts of questions of folks. And if you have an idea, please put up your hand, because it will help me determine how much time to spend on that topic. So the idea is when we're estimating the area of something like this, we're going to sort of use the same approach as we used when we did this area, right? To calculate this area, we can cut it up into triangles, calculate the area of each triangle, add them together. This sort of thing, we're also going to try to estimate the area by cutting it up. Here we're going to cut it up into vertical strips. So I'm going to take some scissors and I'm going to cut it here, and 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 here. Great. So now I've got a bunch of vertical strips. Now if I want to calculate the area of, let's say I want to calculate the area of this vertical strip. Well, that vertical strip looks like that, right? That's what the vertical strip looks like. It's got approximately the same area as this blue rectangle, right? The areas of those two things are pretty close together. So, and a rectangle is something whose area I can calculate. So if I want to approximate the area of this guy, I can cut it up into each strip. And if I have a strip like this, I can approximate that strip with a rectangle like this. I can calculate the area of this rectangle, and I can do that for every single strip, and I can add the areas together. So, and that can give me an estimate for the area. Any questions about this sort of philosophy of cutting something into strips? Calculating the area of each strip and estimating it that way. Okay. So the width of this rectangle is really easy to measure, right? The width of this rectangle is always going to be the same as the width of the strip, right? Because they're vertical strips, they have the same width all the way down. So we know how wide the rectangle is going to be. The problem is going to be, how do we measure the height of the rectangle? And the idea is, if we have, let's say that black thing is a vertical strip. There's three possible rectangles we could use to approximate it. We could measure the height of the rectangle at the left edge of the vertical strip and create this blue rectangle. We could measure the height of the rectangle at the right edge of the vertical strip and create that green rectangle. Right? That green rectangle could be something else we could use to approximate it. Or we could measure the height in the middle of the vertical strip and produce that red rectangle. So the blue rectangle is called a rectangle created using a left endpoint. The green rectangle is called a rectangle created using a right endpoint. And the red rectangle's a rectangle created using a midpoint. Right? So the question when you're talking about left endpoints, right endpoints, and midpoints is the question of where do you measure the height to create that rectangle. Do you measure the height at the left edge? Do you measure the height at the right edge? Do you measure the height in the middle? And those three different philosophies of how to approach calculating this area will give you different results. And sometimes it's more useful to use one, sometimes it's more useful to use another. Any questions about this before we move to the next slide? Okay. So the idea is that this idea that I have up here can be turned into a procedure that can be used to estimate the area under any shape. It doesn't have to be a parabola like this. It can be any curve, any function. We can estimate the area between it and the x-axis using the procedure here. One thing to mention, one thing that will come in mind, that we'll need to take in mind when doing this, is the question of where do we start measuring the area, where do we stop measuring the area. The place we start measuring the area is going to be called A. The place where we stop is going to be called B. So we're always measuring the area. If we have, for example, here's the curve y equals e to the x. Maybe we want to measure that area, right? This point A is where we're going to start measuring the area, B is where we're going to stop. And this green area is going to be the area we're going to measure. So every time we're measuring an area, we all have to know where are we starting the area, where are we stopping the area, what curve are we measuring the area under. So the procedure we're going to use to approximate or estimate the area of this thing is going to be as follows. First, we want to figure out how many rectangles are we going to use. Turns out more rectangles gives you a better approximation, gives you a better guess. Fewer rectangles is easier to do. Usually if I ask you to do something like this, a question in a textbook or in a test or whatever, I'm going to say use 4 rectangles, use 10 rectangles. Right? I'm going to say how many rectangles you need to do. Well, whatever that number of rectangles is, you use that number to divide it up. Divide up this interval into that many pieces. So if I wanted you to use 4 rectangles here, I would divide up the interval from A to B into 4 pieces, right? 1 piece, 2 piece, 3 piece, 4 piece. Each of those pieces, this one, this one, this one, and this one, is called a subinterval. It's basically a piece of this distance from A to B. Then I've got to determine, are we using left endpoints, midpoints, or right endpoints to draw the rectangles? If I'm using left endpoints, I'm going to measure the height here. Oh, I was going to use blue. If I'm using left endpoints, I'll measure the height here for that rectangle, the height here for this rectangle, the height here for this rectangle, and the height here for the last rectangle. So those blue pictures are the rectangles I get if I use left endpoints in that situation. If I use right endpoints, I'm going to measure the height here for the first rectangle. I'm going to measure the height here for the second one, the height here for the third, and the height here for the fourth. So that red picture is what happens if I use right endpoints. And again, usually if I ask you a question to estimate an area, I will specifically say, do it using left endpoints, do it using right endpoints, that sort of thing. Once you've located, okay, I'm using left endpoints, or here I'm using right endpoints, then you measure the height at each of those points. So we can measure the height at each of the left endpoints, or the height at each of the right endpoints. And then after you've measured the height of the strip, if you want to find the area of each rectangle, you've got to find, okay, what's the height times the width? 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 Take all those areas, add them all up. So this procedure is the procedure we're going to use when estimating areas using rectangles. Any questions about this procedure before I move on to examples of it? Okay. So, I'm now going to do some examples. So, the first thing to mention is that this question involves a graph which is given in the textbook on page 369, which I'm going to sketch up on the board in order to do this question. So the graph goes up from 0 to 12. I'm just going to plot some heights. So at 0, it's up at 8. At 2, it's a little bit below 8. At 4, it's a little bit farther down, closer to 7. At 6, it's a little bit above 6. At 8, it's just below 6. At 10, it's at 4. and at 12 it's at 1. So the curve looks something like that.
I think it starts at 9, 0, 9.
Oh, is it not? That's why, maybe why it's off. You're right, it starts at 9, thank you. It's like, why does this part of the curve look off? That's why. It starts up here, 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 here. There we go. Yeah, so if you have your textbooks, you can pull out the actual picture of that curve. That's going to be more accurate than the one that I've drawn on the board. But the idea is we want to estimate the area of this thing using 3 different situations. The first one I'm going to do is using left endpoints. Second one using right endpoints. Third one using midpoints. So what I'm going to do when I do this is I'm going to create a table down here. Oh, sorry. So first, what are the subintervals I'm dealing with? Well, there's one from 0 to 2. There's one from 2 to 4. There's one from 4 to 6. There's one from 6 to 8. There's one from 8 to 10. There's one from 10 to 12. Right? There's this one, this one, this one, this one, this one, and this one. There's 6 different subintervals because there's 6 different rectangles. I'm just going to show little red lines to show which one is which. So the first one, I want to use right end points. So, what's the right end point of the first interval? It's 2. What's the right end point of the second? It's 4. What's the right end point of the third? It's 6. Right end point of the fourth is 8, 10, and 12. Right? So identify what the right end points are. Measure the height of each rectangle. And again, we're always measuring the height at the end point. So if the end point is 2, we're measuring the height at 2, which is approximately, let's say, 8.7. Here, we're measuring the height at 4, which is approximately 8.1. Here, we're measuring the height at 6, which is approximately 7.1. Here, we're measuring the height at 8, which is approximately 5.8. Here, we're measuring the height at 10, which is approximately 3.9. And the height at 12 is approximately 1. So this is the height at each of those right endpoints, right? So this gives you the height of that rectangle, this gives you the height of this one, this is 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 the height of that one. Then, we've got the height of each rectangle, we can calculate each one's area, right? The width of all of these rectangles is 2. So for this area, we're doing 8.7 times 2, which is 17.4. Here we're doing 8.1 times 2, which is 16.2. Here we're doing 7.1 times 2, which is 14.2. Here we're doing 5.8 times 2, which is 11.6. 3.9 times 2 is 7.8. 1 times 2 is 2. And then we can take all those things, add them together to get the total area. Grab my calculator. $17.4 plus 16.2 plus 14.2 plus 11.6 plus 7.8 plus 2. 69.2. So that's the estimate we have for the area under this graph, and that's the estimate we get if we use right endpoints. Part 2 asks us to redo this whole thing using left. Oh, Oops, I just did 2. Oh boy. Okay, I'm going to do 2 first and 1 second. So next, I'm going to do it using left endpoints. Well, the graph's going to stay the same, so I can erase this. Right? Intervals are going to stay the same. Where things are going to change is this line here. Rather than talking about right endpoint, now I'm talking about left endpoints. The left endpoint of this interval is 0. Left endpoint of this one is 2. Left endpoint of this one is 4. Left endpoint of this one is 6, 8, and 10. So now here, rather than using the height here for the first rectangle, now I'm going to use the height here for the first rectangle. The height there, rather than being 8.7, is 9. The height here, rather than being 8.1, is 8.7. The height here, rather than being 7.1, is 8.1. The height here, rather than being 5.8, is 7.1. The height here, rather than being 3.9, is 5.8. And the height here, rather than being 1, is 3.9. So rather than drawing the rectangles using this point, this point, this point, this point, this point, and this point, I'm drawing the rectangles starting using this point, 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 using this point. So those are the rectangles I'm using when I'm using left endpoints. I'm measuring each rectangle at the left edge of the interval. So there I've got the heights. I can use those heights to calculate the areas. Again, here, since the width is 2 each time, we're multiplying by 2 to calculate the area. 9 times 2 is 18. 8.7 times 2 is 17.6. 8.1 is 16.2. 7.1 is 14.2. 5.8 gives you 11.6. 3.9 gives you 7.8.
Yeah, so 8.7 times 2.
Oh, 4, yes. Thank you. Thank you for correcting me. I would have mentioned it. And here, if you add those up, you'll get a total area. 18 plus 17.4 plus 16.2 plus 11.6 plus 7.8. 71. Any questions about what I did here when I used left endpoints instead of right endpoints? Okay. So in part 3, I want to do the same thing, but rather than using left endpoints, now I'm going to use midpoints. So again, I'm going to start with the same graph. They have the same set of intervals. But here, the midpoint of the first one is 1. The midpoint of the second is 3. The midpoint of the third is 5. The midpoint of the fourth is 7, 9, and 11. Right? For each interval, I'm taking what's halfway between. What's halfway between 0 and 1? 0 and 2, it's 1. What's halfway between 2 and 4? It's 3. What's halfway between 4 and 6? It's 5. What's halfway between 6 and 8 is 7, etc. So then I'm going to measure the height at each of those points. So here, I'm going to measure the height at 1. And again, if you pull out your graph, the height at 1 there is about 8.8. Here, we're going to measure the height at 3. The height at 3 is about 8.5. Here, we're going to measure the height at 5. The height at 5 is about 7.2. Wait.
Look higher.
Yes, you're right. That's 7.7 or 7.6. Yeah. Again, You may get your answer slightly different than mine if you estimate it slightly differently. That's not going to be important in these questions. As long as you're approximately correct, that's good enough. Your height at 7 is 6.5. Your height at 9 is 5, pretty much. And your height at 11 is 2.6. And so then, again, if you got the, and so then these are going to be rectangles, right? You draw a rectangle of that height, a rectangle of this 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 height, and a rectangle of that height. And then for each of those heights, we can calculate an area. This will give you 17.6. This will give you 17.0. This will give you 16.4. This will give, no, 15.4. This will give you 13. This will give you 10. This will give you 5.2. And if you add those all up, that'll give you another estimate for the total area. Which is 70. Okay, I must have added up this one wrong.
I think you forgot to add 14.2 to the last one.
Thank you.
I got 85.2.
Thank you. Okay. That one should have been 85. Thank you for keeping that written down because, yeah, that was totally my mistake. I knew this was supposed to be bigger than this. I forgot how much bigger. This one is 78.2, right? So again, we've got 3 different estimates for the total area using 3 different methods. I was just going to ask if there's any questions about what I did here before I move on to the next. Oh, sorry. Is that, no, that's the next question. Any questions about what I did here before I move on to the next example? Okay. So again, I know the previous classes of this I've taught before, I've had students who've had particular difficulty doing these sorts of calculations because they can't figure out how to use right endpoints, left endpoints, and midpoints. Again, it helps to write out what all the intervals are, figure out what the right endpoint, left endpoint, midpoint, each interval is, measure all those heights, multiply by the width, add all the answers up. And that'll give you an estimate for a total area. Okay. The second example I'm going to do I'm not going to do left endpoint, right endpoint, midpoint. I'm just going to do one of them. I'm just going to use right endpoints in this case. And here I want to sketch the area under the graph of f of x equals square root x. So the graph of square root of x looks like that. Sorry, I realized I forgot to copy something down with the slides. From x equals 0 to x equals 4, the thing that's not on the slides. So again, in this sort of situation, you need to know where you're starting your area and where you're ending your area. So start at 0, they're going to end at 4. So here's the region I'm going to be using. So when doing these calculations, the first thing to do is to figure out what the intervals are. Well, here I'm using 4 approximating rectangles, so I'm going to divide this interval up into 4 pieces. I'm going to cut it in half and cut each of these pieces in half, right? 1, 2, 3, 4 intervals. Middle is 2, this is 1, this is 3. So the intervals here are 0 to 1, 1 to 2. Oh, sorry. Let's write those here so I have more space. 0 to 1. 1 to 2, 2 to 3, and 3 to 4. Next thing I've got to do is in each interval, I've got to pick the right endpoint. So here it's 1, here it's 2, here it's 3, here it's 4. Now the key thing here is you could, of course, use a graphing calculator to come up with a really accurate graph of this, which is great. But if you don't have a graphing calculator, you can still do a question like this. And the way you do it is you can figure out what the height's going to be using the fact that this is the graph of square root of x. Right? If you want to measure the height at 1, right, when x is 1, the y-coordinate is going to be square root of 1, right, because the function is square root of x. So here, when we're measuring the height, for the first one, I'm going to take the square root of 1. That gives me 1. Here, the x-coordinate is 2, y-coordinate is going to be square root of 2, because y is the square root of x. So here, square root of 2 is approximately 1.4. Here, at 3, that point is 3, comma, square root of 3. So the height here is going to be the square root of 3, which is approximately 1.7, I think. Yeah, 1.7. Here we're using 4. Well, the square root of 4 is actually 2. Again, if you want to measure the height at that point, the y-coordinate, I'm just going to write a square root of 4 there, but the square root of 4 is 2. The idea is if we know what the function is, we can always find the y-coordinates by plugging them into the function. Take whatever endpoints we're using, plug it into the function to get the heights. If you want to measure the area, well, you're just going to multiply by the width, which is 1 here. So multiply 1 by 1, we get 1. Multiply 1.4 by 1, we get 1.4. 1.7 by 1, we get 1.7. By 2 by 1, we get 2. We add those all up. The total area we get is, I think it's 6.1.
It is.
Yep. Yep. So that's the estimate for this area under the graph of square root of x. It's going to be approximately 6.1. By calculating all these rectangles and adding them up. Again, we can, now, here, the question also wants you to sketch the graph and the rectangles. So again, because we're using the right endpoint here, that's the first rectangle. Right endpoint here means that's the second one. Right endpoint here means that's the third one. Right endpoint here means that's the fourth one. And by looking at the picture of the rectangles, we can determine, is this an underestimate or is this an overestimate? The question really is the rectangles are the estimate. Is the estimate under the graph or is the estimate over the graph? Well, here the rectangles are over the graph. So it is an overestimate. So it's an overestimate because rectangles are bigger than the graph. One thing to mention, a lot of students tend to think, oh, whether it's an overestimate or underestimate depends upon whether you're using right endpoints or left endpoints. It does depend upon that, but there's no hard and fast rule. You have to actually look at what the rectangles look like to figure out if it's an overestimate or an underestimate. You have to look, are the rectangles above the graph, are the rectangles below the graph?
Would it be based on the increasing, decreasing
Exactly.
properties or concavity?
Yeah, increasing, decreasing properties is what's going to be important there. But if something's increasing somewhere and decreasing somewhere else, then it's even more complicated than that. So you just have to look at the rectangles. Like that's the easiest way to do it, is just look at the rectangles. Because even sometimes when it's increasing and then decreasing, the rectangles will still all end up being above, depending on what it is. So again, it's an underestimate if the rectangles are smaller than the graph, and an overestimate if the rectangles are bigger than the graph. So any questions about this example? So one thing to mention about this procedure, sometimes it can take a fair bit of time, but it shouldn't be difficult. If you understand what the procedure is, it should not at all be difficult to do. It just sometimes is time consuming. Okay. So Want to mention a couple things about notation, because I think that what people find the hardest in this section is the symbols that the book uses. The thing I want to mention is if you understand what the question's asking, you don't even need to use the notation, but the book does use it. So the book uses 3 different letters depending upon whether we're using left endpoints, right endpoints, or midpoints. We use L for left endpoints, R for right endpoints, M for midpoints. There's also sometimes a number that comes after that. The number is always the number of rectangles. So if they talk about R10, if they say find R10, it means find the estimate using right endpoints and 10 rectangles. The other notation the book uses are these x's with little numbers under them. x0, x1, x2, x3, x4, x5, etc. The idea is x0 is always where you start. Let me erase this just so I can label these points. So if you're going from 0 to 4, 0 is x0, 1 is x1, 2 is x2, 3 is x3, 4 is x4. x0 is the beginning, xn is the end. They're numbered in between like that. If you had the intervals from 0 to 10, and you were using 5 rectangles, so like that, 0 would be x0, 2 would be x1, 4 would be x2, 6 would be x3, 8 would be x4, 10 would be x5. The other notation they use, sorry, I should give you the next paragraph, is x's with a star on them. The star refers to the sample point. So the x0 up to x5, those refer to the places where we're cutting the number line to create the subintervals. Remember, I sort of mentioned that within each subinterval, we either have to pick the left endpoint, right endpoint, or midpoint. That's what's called the sample point. Where are we measuring the height? So if we're measuring the height at the midpoint, then the midpoints are these guys, x0 star, x1 star, x2 star, x3 star, x4 star. No, x1, you don't start with x0 with the sample points. You start with x1 with the sample points. I'm sorry. 1, 2, 3, 4, 5. There's no x0 star. Anyways. Now, the thing to mention about this notation, it's in a number of the questions in the book. If I'm giving you questions on a quiz or a test, I will not likely be using this notation. So you don't have to worry too much about it. But if you're reading the book and you're having a difficult time understanding it, this is what's going on. But yeah, I will try to avoid this as much as possible because I find that it just confuses people more than it helps them. Any other questions about this before I move on to 5.1.2? Okay. So, the second half of section 5.1 is taking this approach we've used to estimate area and turning it into an approach to calculate area by using the idea of a limit. Right? Again, limits are something you talked about in Calculus 1. The idea is a limit is what happens when a number approaches something but doesn't quite reach it. And the idea is we can use this limit idea to explain how the area we can build with these rectangles is going to approach the actual area but never quite reach it. So we're going to be able to write limit expressions, write formulas with the limit sign in front of them that will allow you to give the area between a curve and the x-axis. Is there anyone here who feels comfortable doing this because they've learned it before? One person? Anyone here? Yeah, 2 people. How many people here have done it before but totally don't feel comfortable doing it? Totally forgotten it? I see a couple of people. How many people have never done anything like this before? Okay, that's more of the class. And then everyone else is just too shy to put up their hands, and that's okay. So, what I'm going to do is I'm going to show what happens when we use more and more rectangles. One thing to mention about the estimates that we've come up with is these estimates are not particularly good. You'll notice that these 3 ones I've come up with, 69.2, 85.2, 78.2, they're pretty far apart, right? Like 69, you know, like I know, of course, the area is going to be somewhere between 78 and 85, but I don't know where between 78 and 85. But probably close to, no, sorry, between 69 and 85. Probably close to 78 because it's, you know, sort of in the middle, but really I don't know it all. So these estimates are not always very good. If you want to come up with a more precise estimate, if you want to come up with a better estimate, what you really need to do is you need to use more rectangles, right? So far we've only been doing like 6 to 8 rectangles because that's how many we can do by hand. If you've got a computer, you can do it with 1,000 rectangles. And that's what I'm going to be doing now, is showing you what happens when we use lots of rectangles. So, hopefully this will work. This is my Java's not up to date on this computer, so it's loading. Anyways, Java's loading, great. Okay, so once the Java's loaded, I can actually show you what's going on. Yes, I want to. It's not a security risk, I know where this comes from. There we go. So, now let's look about this one. Okay, so here we have a curve, right? And let's say we want to estimate the area under the curve. Oops, sorry, I've got to scroll down. The curve here is x squared. It's a parabola. So let's say I want to use 10 rectangles, right? If you use 10 rectangles in the midpoint, it's going to look like that yellow thing. 10 rectangles in the left endpoint looks like that one. 10 rectangles in the right endpoint looks like that one. And if you go, there it is. Now scroll to the right place. So if you use left endpoint, you get 0.285 as a sum. Up in this upper left-hand corner is where it shows the answer. Here it gives you 0.285. If we use 10 in the left, 10 in the right gives you 0.385. 10 in the midpoint gives you 0.3325. Again, those numbers are still fairly far apart. However, if rather than using 10 rectangles, we now use 100 rectangles, what we'll notice is that now that we're using 100 rectangles, these rectangles are very close to the curve itself, right? There's a little bit where the rectangles stick above, there's a little bit where they're below, but they're almost exactly on the curve. If we use 100 rectangles and the left endpoint, we get 0.328 up in the corner. 100 in the right endpoint, we get 0.338. 100 in the midpoint, we get 0.3333. Right? Those numbers are all around 0.33, so those numbers are all getting a lot closer together. If we use even more rectangles, let's say we use 1,000 rectangles, you'll notice now you can't even see the difference between the rectangles and the curve itself. They've sort of all gone exactly to the curve. If we do left endpoint, we get 0.3328. Use right endpoint, we get 0.3338. Use midpoint, we get 0.333325. Can anyone guess what the exact answer is for this one?
1/3.
1/3. The idea is the more rectangles we use, actually it just says up there, I just realized, the more rectangles we use, the closer and closer these numbers get to 1/3. The closer and closer these numbers get to 0.33333. So what we say is that to calculate the area, the exact area, we can take the limit as the number of rectangles goes to infinity of the area of that number of rectangles. So the idea is as the number of rectangles goes to infinity, this area gets closer and closer and closer and closer to the exact area of the curved shape. If you want to play around with this and sort of play around with other shapes, do left endpoints, right endpoints, and midpoints. The link here is in the slides that are online. But that's the key thing, is the exact area is going to be the limit as the number of rectangles goes to infinity. Any questions about this idea before I move to the next slide? Yes?
So when it comes to left endpoints, does it always have to be on the graph?
Yes, that's what makes it, you're always measuring the height from the graph is always what you're using to measure the height.
So it doesn't necessarily have to be on the graph?
Maybe see, okay. If the graph looks like this, and you're doing left endpoints, you pick the left endpoint of the first one, you go up to the graph, measure the height. Pick the left endpoint of this, go up to the graph, measure the height. Left endpoint of this, go up to the graph. So you're always using the graph to measure the heights of the left endpoints?
I think I just do this one.
And if you're using the heights of the right endpoints, you're always still using the graph to measure them. It's just whether you're using the graph here or you're using the graph here to do the first rectangle.
And for the right endpoints, it will also be so that
Also be always on the graph, right? If you're using the right endpoint, it's going to be this one go across. This one go across like this.
So the right endpoints would be an upper sum.
Nope. Look at this one. Here I'm using right endpoint going across. Here I'm using right endpoint going across. So no, right endpoints are not always upper sums.
Not always, but in this case, is it?
Only if I was going from here to here, the answer is yes. If I was going from here to here, the answer is no. It's underneath, right? So no, it depends upon, and again, it's sort of. Where's my list of names? I was going to say. I don't know if. I'm trying to. Is it Daryl? Yeah, great, good. You are sitting in the same spot as last time. I was like, I think it's Daryl. Yes. So what Daryl was saying earlier about being increasing and decreasing, I think that was you, right? You're talking about increasing. Anyway, so whether it's above or below, whether it's an upper sum or a lower sum, depends on whether it's increasing or decreasing.
Will we get a question or something like that?
I wouldn't ask whether it's an upper sum or a lower sum in a case like this because you can't actually figure it. Unless you can tell whether or not this amount above is bigger or smaller than this amount below, you can't really tell. Yeah. You're welcome. Okay. So the next thing I'm going to talk about is what the notation is that we use when we try to write these limits. The limit is the number of rectangles goes to infinity. The first thing to mention is when you're calculating the area, you're calculating the height at a bunch of different places. You're multiplying each of these heights by the width, and you're adding them up. These points, x1 star, x2 star, xn star, those are all the points where we're calculating the height. If you want to calculate the height, I don't know if you remember with the square root example, to calculate the height, you plug it into the function. So f of x1 star is the height at x1 star. F of x2 star is the height at x2 star. F of xn star is the height at xn star. Delta x is a symbol for the width of the interval. So the idea is if you want to measure the area of all rectangles put together, you can write it out using this formula. This is the first height times the width, plus the second height times the width, plus the third height times the width, plus the fourth height times the width, until we get to the nth height times the width. That's what that formula represents, is taking each of the heights, multiplying by the widths, adding them up. When we write this thing out, we're going to use what's called sigma notation to abbreviate this. Rather than writing x1 star, x2 star, x3 star, x4 star, keeping on going until we get to xn star, we use this symbol, sigma I equals 1 to n. That symbol means we're doing it for every number between 1 and n. We're taking all the numbers from 1 to n, and we're plugging them in. That's what that symbol represents, and we're adding them up. So rather than writing up the sum like this thing up here, we oftentimes write it like this. Sigma I equals 1 to n of f of xi star times delta x. So that's sort of the symbol we use to represent what we get when we add up all those areas. Calculate the area of each rectangle, add them all up. Again, this says we're doing it for all the numbers between 1 and n. For each number between 1 and n, we're taking that sample point, evaluating, plugging it into the function, multiplying by the width. That's what that symbol represents. Now, if we want the number of rectangles to go to infinity, we put a limit and then goes to infinity symbol in front of this. So this formula is basically the formula for calculating the area as a limit. This formula says we're taking the limit as the number of rectangles that goes to infinity. We're adding up all the rectangles from 1 to n. For each rectangle, we're calculating the height by plugging it into the function. We are multiplying by the width. That's what this formula represents. Again, in this course, I'm not really going to get you to do much with that formula other than write it out. So if you're having a hard time understanding what xi star is, what delta x is, we'll talk about a little bit more about that later. But the key thing at this point is going to be able to understand that this is the formula that you use when you are calculating the area as a limit. When you're taking the limit as the number of rectangles goes to infinity. That's the formula to use. Any questions about that formula before I move on? How many people, by the way, with that sigma notation there, how many people have used, is there anyone here who has not used this ever before? Okay, there are a few. How many people have used it before but forget how to work with it? Is there anyone here, how many people here feel really comfortable with this? Okay, I see more people that are really comfortable with this camp. I will sort of go over some examples of how to work with this when I get to 5.2. And I'll sort of go into that in a little bit more depth just to help those folks who haven't seen this before or aren't clear what it represents. Okay. So, the idea is the goal of this section is to be able to write a formula for the area as a limit. To be able to write out a formula which represents the area of a certain shape using limits. So one thing to mention is in 5.2, we'll talk about how it's easier to evaluate these limit statements if we can actually find a formula for xi star and a formula for delta x. There are these two formulas down here which we'll always use to represent xi star and to represent delta x. Delta x is the width of each interval. If we want to find the width of each interval, all we've got to do is take how long is the place where we're evaluating the area. Here it's 4 units long, and divide that by the number of intervals. So to measure how long it is, we take the right end minus the left end. B minus A tells you how long it's going to be. Dividing it by n divides it up into the right number of pieces. So that's the formula for delta x, is B minus A over n. The formula for xi star is A plus I delta x. A is always where you're starting to measure the area, the left edge. Delta x is the width of the interval. I is telling you how many times we go right by delta x. So if I is 2, we're going to go right 2 times. We're going to get x2. If I is 4, we're going to go right 4 times. 1, 2, 3, 4. We get x4. That's where those formulas come from. Again, if you want to just sort of memorize those formulas and use them, you completely can. You don't really need to understand where they come from to use them. But they are going to be important when writing out limit statements. So, example 3, I am going to use all the ideas I've shown in the last few slides to write an expression for this area as a limit. So the area we're talking about is the area under the curve f of x equals x squared plus square root 1 plus 2x for x between 4 and 7. So I'm just going to quickly draw a picture of it to show what area I'm talking about. The curve, x squared plus 1. The curve looks something like that. We're talking about what's happening between x is 4 and x is 7. So we're talking about that area there. The first thing when trying to write out an area like this is to write out that limit statement on the previous slide. Right? We're always taking the limit, as n goes to infinity, of the sum, I equals 1 to n, of f of xi star delta x. Right? This is basically the formula we're always going to be using to express the limit of a sum of rectangles. Now, we can fill in some of the things we know. Xi star, first delta x. Delta x is always b minus a over n. B, the place we stop calculating the area, is 7. The place we start is 4. So delta x is 3 over n. Xi star is going to be a plus I times delta x. A, the place we start, is 4. I is just I. Delta x is 3 over n. So xi star there is going to be sorry. And we can do one more step for writing out this limit statement. And that is when we're doing f of 4 plus 3 over n, what we're doing is we're taking 4 plus 3 over n, we're plugging it into this formula. Right? This is the formula for f of x. So I'm going to have 4 plus 3 over n squared plus square root 1 plus 2 times 4 plus 3 over n. This is f of xi star. And then we multiply that by delta x. Multiply that by 3 over n. And this now is a limit statement. This is a statement which says what this area is going to be, and it's written out as a limit. It's basically, wait, there's an I missing. There's an I here. I'm going to write it as 3I over n, actually. That'll fit a little bit, but I times 3I over n is the same thing as 3I over n. I was like, wait, there should be an I in there. We will learn in section 5.2 how to actually evaluate a limit statement like this, how to figure out what this limit actually goes to. For now, what I'm going to concentrate on is how do you write that sort of thing out? How do you use this idea of area of rectangles to write out a limit statement like this? And the idea is what you need to know is you need to know basically this formula, how do we sort of express an area as a limit? How do we figure out what delta x is? How do we figure out what xi star is? Okay. So it's time for your break for 10 minutes. So it's 12:41 now. Oh, I said 3:41. Come back at 12:51, and we'll start on section 5.2 at that point. Again, I'm pretty confident I'm not going to make it to 5.2.3 today. I'll just be doing 5.2.1, 5.2.2. So yeah, take a 10-minute break.